Okay. So I know somebody is joined. Valerie is joined. Let me just. All right. So we go back here. All right. So this is being recorded for those of you that are not here today. And everybody in the room decided that today should be the +10 day. So I'm deviating. So we'll see how it goes. Listen in carefully, and the decision will be made at the end of class. Okay. All right, recap questions. What is saponification value used for? All right, Paige.
It's used for the identification purposes, especially if that main fatty acid that's in the oil.
Absolutely. It's a good identification, authentication, and often the value is used to confirm the average molecular weight of fatty acids in oils. Usually different oils have unique profile with a predominant fatty acid, like olive oil has a predominant oleic acid content. Canola it's linoleic acid. Corn is linoleic for short. Okay, if oil A has higher saponification value than B, which one has lower average fatty acid molecular weight? Yes, Chinyu? B has lower. Does anybody disagree to that? Yeah. You're just gonna say A. Is anybody gonna explain why? Of course, it's not B. If it's not B, it's A. But do you remember the equation? I want you to remember this, because this could be something I asked in the final, most likely. Okay. All right, so what do we have? We have 1 mole of triglycerides reacting with 3 moles of KOH. And the saponification value is milligrams. So saponification value is milligrams of KOH that saponifies a gram 1 gram of fat. Okay, and we know that molecular weight is grams per mole. Okay. The higher is the molecular weight, the less they're going to be grams per mole. It's large, right? So the higher the molecular weight, the 1 mole will have less. Okay, let me say it in a way that makes sense without confusing you. I would say there will be less number of moles in a gram if you have large molecular weight. Is that better? Does that make sense? I said it incorrectly. So if it's a large molecular weight, there will be less number of moles per 1 gram of sample. So because there will be less number of moles per 1 gram of sample, I will be needing less KOH to saponify, because 1 to 3 moles. So when I have lower molecular weight, I will have more moles per 1 gram. So I will need more KOH to react because of reaction is based on number of moles, reacting with number of moles. Right? So it's an inverse relationship. So more numbers of moles in 1 gram of fat if low molecular weight. So I will carry more number of moles if I have low molecular weight fatty acid in 1 gram of fat. If I have more number of moles, then I need more KOH to saponify that 1 gram of fat. That's why it's inverse relationship. Okay. Which test is used when testing efficiency of hydrogenation? Remember? What happens during hydrogenation, Zoe?
The iodine value.
Yes, because the iodine value is a measure of degree of unsaturation. During hydrogenation, we hydrogenate. So we add hydrogens to the double bonds. Yes? How? Are they going through my calendar?
Yeah.
What do they get? What error do they get?
They said that they are in the waiting room.
They are in the waiting room?
Yeah.
I didn't even know that I had a waiting room. Where do I find? That's me. What's that? How do I find out? How do I know if I have waiting room?
Little down arrow on the button.
Here?
Over to the left. Yeah, the little arrow.
Or if you just hit participants, and let's just see. Yeah, so no one's on it yet. Yeah, that's what
Yeah.
they said.
Breakout rooms? I don't have breakout rooms. Do you want to send the link to people in an email? You
The
can
link on your
get the
Google
Zoom
Calendar?
link. It's on my calendar.
Okay, let me try to see if I can access it.
Yes, that would be good. No. Maybe it should maybe tell them to log into their U of M. If they go to my U and log in, then they can access Zoom. If they're not logged in, maybe they can't. Essentially, that's what it is. Okay. All right, so presence of free fatty acid is an indication of what, Paige? Yes. Was that
Sorry, I was
what
gonna
you?
ask you about the second question. If you could just, so
Which test is used when testing efficiency?
No, the one before that. So it would be oil A.
If
then
oil
with the
A
lower
has
value.
higher saponification, then oil A will have lower.
Then, okay,
Yeah.
great.
Okay. Okay, so when the presence of free fatty acids is an indication of what? Yes, there. Hydrolytic rancidity. Yes, that's one. What else? Yes. Age of the frying oil. Absolutely. Because during frying, triglycerides might break into fatty acid due to high heat and high moisture. Okay, what else? Yes. Efficiency of refinement. When you are refining the oil, you're getting rid of free fatty acids. You don't want free fatty acids because they cause off flavor, they oxidize fast. So refining takes care of free fatty acids. And why do we sometimes have refining have free fatty acid? Because sometimes you have endogenous lipases in your crop, in your grain.
Sorry.
So what is giving?
So I'm having the same issue.
So maybe you can try sending me a link personally, and then I can share it
Okay,
to.
let me. So that's very, very strange. And I'm signed to Zoom. I'm in Zoom. Okay.
Can you create a new link?
That's no trouble. Okay. So copy link. Okay. And okay. Okay, so check now. Still giving you the same?
No. I
You
haven't
can-
received the link.
Did you, you have to close out of this.
Maybe it's like your privacy setting. Can you set it like to open to anyone or
So,
if you go on Zoom, maybe like the actual Zoom call?
okay, so go here.
Maybe edit. Required authentication. No waiting room. How do you remove that? Maybe under settings or
Where?
meeting options, scroll down. I don't see anything. Maybe under settings.
Allow. Ah, I can't do anything here. Where's the setting? Oh, setting.
Waiting room.
It's not
It's
on.
not.
Require a passcode when scheduling meetings. Require passcode for instant meeting. Or no, require passcode.
Let me authenticate. No. Wait.
Yeah. Let's see. Are you logged into Zoom yourself?
Yeah, I am. Even Laura tried. And
I don't know what else to do. Because I'm recording, I don't want to stop the recording and go back and record another one.
maybe I can set up a personal Zoom call on my laptop.
It's okay. They will just listen to the recording. I don't know
Okay.
how to do it now. I need to continue the
Yeah,
lecture.
yeah. Okay.
Yeah.
I'll let.
I don't know what happened and why it's doing that.
Yeah, sure. It just says that it's not a Zoom meeting. So
That's weird.
probably something in the video call settings.
Yeah.
It's fine.
Oh my gosh, now it's not working. No. Okay. All right. We're gonna skip that. You guys can name them on your own. We need to move on. Okay, so free fatty acids. So It's a measure of fatty acids liberated upon hydrolysis of triglycerides. So in crude oil, sometimes we have free fatty acids, I was saying, because you might have endogenous lipases in the seed that might hydrolyze triglycerides and free fatty acids. So when fatty acids are freed, they contribute to off flavor, they can get oxidized, so we don't want that to happen. And sometimes we have hydrolytic acidity during storage of grains or flour, so that can happen because of the fact of you have endogenous lipases. It's also an indication, like I said, of frying of the oil. So you want to remember that when I ask you about free fatty acids. So because they're acids, so it's the easy way to quantitate them is by titration with a base, because they're acids. So it's very easy. You'd have a sample, you add an indicator, a phenolphthalein indicator, I believe, to your acid, to your fatty acid, or whatever oil you have that might have free fatty acids. You titrate with 0.1 normal NaOH. So you have the normality of NaOH. And in this case, it's sample minus blank. So you run a blank. If the blank will not have free fatty acid, you will have very close to a 0 to correct for any potential acids that might come from different sources. And then the sample would need more volume of NaOH, obviously, to neutralize the acid. And then here it's the molecular weight. In this case, it is oleic acid. So if we're doing free fatty acid in olive oil, we use the molecular weight of the most dominant fatty acid in that oil. And in this case, it would be 282. So it's a percentage. So basically you correct for milliliters to liters by dividing by 1,000. And then you use the weight of the sample. And then you multiply by 100 because it is a percentage. And sometimes when you calculate it using oleic acid, you can convert it to other, if you want to look at palm oil, palmitic acid would be the most common, then you can just use a conversion factor. Or use the molecular weight of palm oil, palmitic oil, palmitic acid. All right, so measuring the present status of oxidation. So here we're going to switch our topic and talk about oxidation, and we're going to talk about measuring the current status of the oil versus measuring the status of or the oxidation over time, like shelf life or prediction of shelf life. So peroxide value is a very common measurements for the current status of oxidation. It measures peroxides from the name, peroxide value measures peroxides, which are primary products of oxidation. So you're taking fat, lipid chemistry in food chemistry, so you should know what the primary products of oxidation are. And so you always have to remember what the value measures, so measure peroxide, and how it is defined. It's defined by the unit, so it's milli-equivalent of peroxide per 1 kilogram of sample. So now we have saponification value, which is milligram per 1 gram. We have iodine value, which is grams per 100 grams. And then here you have milli-equivalent of peroxide per kilogram of sample. So every value, it has a different unit. So a freshly refined oil or fat, a very fresh fat or oil will have peroxide value of 0 or very close to 0. How about a very rancid oil? Like extremely rancid, you sniff it and you go, oh. What do you think the peroxide value of that oil would be?
I mean, I don't know the range, but I would assume that the more rancid, the higher the peroxide value would be.
And then what happens when you reach the maximum peroxide value? It's a primary product of oxidation. it converts to secondary products for oxidation. The oxidation continues. You get metabolites out of it. You have secondary metabolites like aldehydes. So you, at the end, it's like a curve, and that's what you're going to see in the lab when you measure peroxide value of oil that has been stored at different time points. The expectation is to see, this is time, this is peroxide value. The expectation is to see a bell shape. So you start with very low if we get an oil that is fresh, but sometimes we purchase oil from the shelf, from the store, it hasn't been really fresh. So we don't know at which point, we don't have access to freshly refined oil. So what we expect as freshly refined oil is that you start here very low and you reach a maximum. So you have peroxide value forming, and then here peroxide value will decrease, and then secondary metabolites will increase. So here the rate of formation of peroxides over time of storage is higher than the rate of formation of secondary metabolites. On this side of the curve, the rate of formation of peroxides is lower than the rate of formation of secondary metabolites. And at one point, all of your oil is oxidized. So there's no more formation of peroxide. You only see formation or continuation of the secondary metabolites. So you might get to 0 here. So a very rancid oil might have a peroxide value of 0. How do we know that it is rancid? Really open the oil and it's going to smell really bad. So even if you have a peroxide value of 0 and the oil smells really bad, you cannot say it's fresh oil. It's a very oxidized oil. So the way we determine peroxides is that if you have peroxides in there, they're going to react with potassium iodide and give you iodine. In the presence of starch as an indicator, you have a blue color. And then you will be titrating with sodium thiosulfate to colorless until all of your iodine are taken up and form sodium iodide. So again, it's titrating to colorless in this case. And because it's in the equivalent milli, so we don't correct for a milliliter per liter. So you don't see 1,000 here. You divide by the weight. You don't need to convert milliliter per liter. And you multiply by 1,000 because it's 1,000 grams. And here it's sample minus blank again in this case, because if you don't have a peroxide, you won't generate iodine. So if you don't generate iodine, your blank will be very close to 0. Okay, if you don't have peroxide. If you have peroxide in your sample, then you generate iodine. The iodine will cause a blue color until titrated colorless. So this is what you're going to do in the lab to determine the present state of your oil, and then what happens to your oil when it's been stored over time. So you'll have your oil sample already oxidized for you over time, so that you can plot a curve like that.
Here, says how like food companies or industry would measure oxidation, or do they use different methods?
Yeah, so I will show you how they would measure oxidation. Yes, the industry will use peroxide value, will also use Totox value. So Totox value here is basically a combination of NCD value that measures the secondary metabolite, unsaturated aldehyde. And it's basically a reaction between NCD and aldehyde to give you a color. The Totox value is a combination of NCD value and peroxide value. So in the industry, we look at multiple oxidation methods, peroxides, secondary metabolites. So it depends on what they're looking for, and it depends if they're looking at shelf life only, they can start with a very fresh oil, and then they store it, and they only can measure peroxide. They don't need to measure a secondary oxidation product. If they are testing the oxidation of an unknown oil, like there is a complaint, and they want to test the current status, they test peroxide, they test secondary metabolites. They have to do that. Yes?
Would that first be able to like use by itself, or would it be like somewhat misleading since that's the secondary oxidation product?
This one is misleading.
No, but are those always used in quantity?
Oh, so if you have secondary oxidation product, that means you have oxidation. You don't care about peroxide. So you already have an oxidation going on, but you want to determine where are you in the oxidation? Is it early stages? Is it mid stages? Is it late stages? So oftentimes you do multiple tests for oxidation. So hexanal is another test for secondary oxidation metabolites. So hexanal is a secondary oxidation product. You can measure pentanal, pentane, these are all secondary oxidation products. So these will be formed and they're volatile. So these, because they're volatile, you can do GCMS using headspace. What does that mean? That means the space above the sample. You put your sample in a glass container, you cover it, and then you let it sit. Then this headspace is saturated with your volatiles. Then you can take a syringe and grasp a little bit of your headspace and inject on GC, and then you can measure the amount of hexanal you have in your headspace, which is an indication of secondary oxidation product, and it correlates well with flavor. So with sensory attributes, because it is a volatile, it contributes to the flavor of your product. So it's a very distinct, has a very distinct flavor. And here you don't need to do lipid extraction. So you have your, let's say your flour sample, you put it in your container, you let it sit to have a saturation of the headspace, and then you sample from the headspace. This is another common oxidation method. We used to teach a class called chemical reactions. And in that chemical reactions, it was additional lab experience where students would do T-bars. So in food analysis, we do peroxide. In the next class, we will do T-bars. So in T-bars, basically pyobarbituric acid reactive species. So pyobarbituric acid is the reagent, TBA, that we use, and it reacts specifically with malonyl aldehyde, which is a derivative of linolenic acid. So the linolenic acid, basically the oxidation of linolenic acid gives you specifically malonyl aldehyde. And this reacts with TBA and then you give you a compound that you can measure at 530. It correlates better with sensory than peroxide. Any method for secondary oxidation correlates better with sensory than peroxide value does. So, however, malonyl aldehyde still can oxidize other components, so it reacts readily with other compounds. It's not a very sensitive method. Alternative method is HPLC to measure directly malonyl aldehydes, and it is used commonly in meat products. So here I'm going to spend a little bit of time to explain prediction of shelf life for different oils. And also this is commonly used to predict the efficiency of antioxidants that we use to enhance the shelf life of oils. Synthetic antioxidant and natural antioxidants sometimes are added to extend the shelf life of the oil or the food product to delay oxidation of lipids. So here there's a term called induction period. So what is the induction period? Here on this graph, you have y-axis, lipid oxidation, and then time of storage. So the oil, for example, or the fat can store well for a certain period of time, and then it starts to oxidize. The induction period is the time it takes from 0 time when it's fresh to X time where you start detecting oxidation. So that's the induction period. The period that the oil remains fresh until oxidation kicks in. So for example, when you use antioxidants food formulation, you want to extend the induction period as much as you can. So that's what we mean by induction period. To determine shelf life of oils, we often do accelerated shelf life studies because we're not going to wait months to determine the actual shelf life. So we abuse the oil. Basically, we store it at high temperatures so that we can generate oxidation and predict shelf life. All right, so there are different ways that we kind of accelerate shelf life, do accelerated shelf life studies. The most common one is oven storage test. And that's what your oil samples will be subjected to. So your oil samples will be stored in an oven at high temperature for several hours, and the sample will be taken out at different intervals. And then you will measure oxidation at each of these intervals. And that's what the oven storage test is. So usually we accelerate it for the lab purposes at really high temperature, but the oven method is usually 60 to 80 degrees C. And then over several days of storage, not hours. For the lab, we need to speed it up, so we abuse it at really high temperature for a few hours. So, but to do that for actual prediction, we use 60 or 80 degrees C, and then we take samples at different days, number of days, and oftentimes we just measure lipid oxidation by peroxide value. So lipid oxidation often is measured by peroxide value in this oven test method. So the second one is oil stability index. So this one here, you take your oil and you heat it to probably over 100 degrees, 110 to 130 degrees C. And you bubble through the oil, you bubble air. So you are actually abusing it by heat and giving it oxygen. And then the organic acids generated from oxidation are going to be sucked up into another container, a flask, and then conductivity is going to be measured. So here we measure the volatiles that comes off of the oil by conductivity. So there is specific equipment that we can utilize for Rancimat that will give you that you can do this oil stability index with. The last one is oxygen bomb. What does it mean? You put your oil in a closed chamber and you pressurize it with oxygen. So it's pressurized with oxygen, and then you put it in a boiling water bath. And then you measure the drop in pressure. The drop in pressure is an indication that oxygen is being uptaken by the sample due to oxidation. So that is another method. But again, the most common one is the first one over here, or the second one, which by Rancimat. The third one is the least common. Now, other than looking at oxidation and rancidity and characterization by iodine value and saponification value, we want to also determine the different fractions of lipids we have. So this is mostly for nutrition labeling. So we need to determine the degree of saturated fatty acids versus polyunsaturated versus presence of trans fatty acid versus presence of cholesterol, presence of phospholipids, these mono, di, and triglycerides that mono and diacylglycerols are used for emulsification purposes. And also looking at lipid-soluble pigments and vitamins. We'll have a chapter on vitamins and then also on measuring the lipid-soluble vitamins versus the water-soluble vitamins. So mostly we use GC methods to quantitate the different fatty acids and cholesterol. And thin layer chromatography is used as a qualitative measure to determine different composition within a lipid sample. So we already know how to determine free fatty composition of fatty acids by the FAME, fatty acid methyl esters method using the GC. You already did that lab, and help with determining composition and also detecting other alterations. Now, cholesterol lipid fraction is saponified. So cholesterol is non-saponifiable matter. It cannot be saponified. So when fatty acids are saponified, they are separated in the aqueous phase and cholesterol remains. So you get rid of the fatty acids and you take the cholesterol that cannot be saponified and then you derivatize it, obviously, because cholesterol is non-thermally stable and non-volatile. But you derivatize it to trimethyl silyl something, TMS. And then you follow GC analysis. So the last thing here is thin layer chromatography. And this is mostly qualitative. They do that in experimental nutrition, the class for nutrition majors. It's actually, I believe it's one of the labs for their blood samples. The students give blood samples and they look at the distribution of these different components in the blood sample. So what usually you have, you run standards. So what you have here is phospholipids, monoacylglycerol, diacylglycerol, free fatty acid, and triacylglycerol. So you have those standards, you run your samples, and you determine what your sample has. So it's very qualitative, and they use in order to see the different fraction, they spray after they run the TLC, they spray it with dichlorofluorescein, so you get the fluorescence and you determine the presence of these different components. So next week in lab, when you come back from Thanksgiving, we're going to bring you back to being groups of 5, your original group of 5, and then you will have corn, canola, coconut, lard, and olive oil, 2 types of olive oil, extra virgin olive oil that will have higher free fatty acids, and refined version of the olive oil. We're going to determine peroxide value on a fresh and stored samples, and you're going to plot something like that to see what happens. Different fats will start at different times. You might see a sample that starts low and keep going, and doesn't come down because it didn't reach the time where you have secondary metabolites formation. You might have a sample that starts high and goes down because it's already oxidized, and so on. We're going to see different schemes of that graph. Saponification and iodine value, you'll be determining that on fresh samples. Each group will have an assigned fat to do that, free fatty acids on fresh samples, and then we'll get the data of all 6 groups to use in your lab report. Read your chapters in the textbook and the lab manual, pre-lab quiz, and bring your lab manual and computers with you. And have a great Thanksgiving, you guys. I'll see you next week. Oh yeah, if you have your +2 sheets, give them to me. If you don't have it, you can bring it on Monday. That's totally fine. So we have 2.
What's the +5 and the slides?
Oh, the +5. Oh, that was the dietary fiber.
Yeah.
Oh.
I have both of them.
Yeah, so let's put them separate for me, guys. You can come do that yourself. And remember, I have posted a +5 extra credit opportunity for factorization. It's on Canvas.
Oh, yeah.
Oh, I shouldn't have that. I don't have my thing. What was I supposed to do here? Oh, okay. Yeah, so I'll tell you, if I tell you your grade, you can send it to me. So when I go to my office, I will put it in my room. So, wow. The whole lab. Oh.
I screwed up. Yeah, I have to read them.
And
That's great. Yeah.
data, your calculation. And you can just discuss them all right up. Oh my gosh. All right. And this. Perfect. You have the ash and fat data. Good. And the protein too. Good. Just send me a note saying I give you 10. So I haven't looked at it. No.
No, because I told you.
Yeah. So 53. Mhm. So, oh, the raw data is your spectrum. The spectrum.
The structure sheet?
Yeah.
Oh, okay.
Yeah, just stick it in there.
Okay.
Calculation. And addition. Yeah. Okay.
Wasn't me. Like when you're
Ah,
sorry.
that's
Because
nice.
a lot of people forget how.
Yeah. Okay, calculation. Okay. Okay, you get 10 plus 1. So send an email with that. Yeah, don't forget to send me an email. Okay?
Wow, for questions.
Yeah.
So we talked about the material. It was like, there was like
Negative.
technically, yeah, it was negative. So
Yeah,
with
there must be something off with the wish.
okay. So for like, and it was like a negative 100, I think. So like,
It's not, it's not, it's not.
So it's
So no,
so I
that-
just put 0.
yeah, not that. And
So I try also, I guess they're precision. I don't know.
I mean, it's just something that's off.
Okay, so let's put it there.
Yeah.
And then, if I'm like, do I cite like the textbook types? Do like a reference to the textbook?
Yeah, if your site, if the textbook, that means you're taking the information from the.
Okay, so I'm doing stuff.
Me too.
That's how you're doing ash and.
Yeah.
So wherever you're talking about ash, you set the ash on the,
Okay.
and.
And then, like, how can we use this book for for question 10? Like the driving space, we use the moisture content for the driving space.
Yes, of that particular sample, your sample.
Okay. And then my last question for the fact is, do you have to put like a line of best fit for the absorption versus or like not too value? Like absorption versus.
Oh, no, that you just block it and it's just showing that no R squared, no equation. No nothing. It's just a plot that shows you maximum absorption.
Okay.
Okay. So I don't know what happened. Oh, I'm still recording, right?
Yeah, I don't know if it has students in